Okay, so welcome to lecture 2 of Shadows of Computation. Uh, I want to pose a question to sort of theme this talk, and we'll talk about the question, and then I will. I guess the aim is to hopefully category theory gives a good answer to this question, and we'll explore those ideas. Okay, so what's the question? When are two mathematical objects the same? And I guess just as a spoiler, like part of the answer uh, is that it's like a component of the answer that category theory gives is that it involves preserving structure. But let me just revisit the question and actually put a question mark on it. And well, I think like a sort of sensible first response to this is that like I don't know, the answer seems kind of obvious. Like just in general, when are two things the same? Well, it's obviously just when you're really talking about one thing. Um, like there's not two things, there's just one thing, and it's the same as itself, obviously. And no other two things are the same because that's the point of being the same. But the sort of lesson with mathematics is that uh, this doesn't get you very far, and it's kind of too strict of a notion uh, of equality or sameness. So, to give a sort of simple example that it doesn't really get to the sort of heart of what happens in mathematics, but just a simple example is uh, I I could refer to me as me or like my father's son. Um, those those two things are the same person. They're the same human being. But I've used sort of different uh, labels or like I've used different means to reference uh, that human being, and so clearly it's the wrong level of analysis to say that like uh, merely using different terms to refer to certain objects makes them like distinct objects. And so the idea in that is that I'm like the when you have a sort of conceptual level um, on which you want to sort of identify when two things are the same, it involves thinking about what is the underlying thing. Um, and the idea is if you can sort of identify this, then you have a system by which, okay, like if you have an X and a Y, like those are literally two different labels. Um, if by their definition they sort of are just different references to this single underlying thing, uh, then like we want to just say that these are the same thing because they're like what we mean is the underlying thing is the same. Um, and so, for example, we could say x equals y if uh, x is 2 and y is 2. And the fact that like x and y are different variables doesn't sort of prevent these things from being the same. Um, and if this was the sort of end of the story, it would all be very simple. But turns out what sort of tends to happen in mathematics is the situation is more like this. We have sort of two descriptions of objects, and typically you have like some framework like ZFC, which sort of gives you uh, sort of a universe for your all of the sort of data to live in. And you might have X referring to one piece of data and Y referring to another piece of data. And uh, at this level, like at the ZFC level, they really are like they're literally distinct pieces of data. Like they're not the same And like even like it's not like this situation where like it's two labels, like you got a variable x and a variable y and they both refer to two. It's two labels referring to distinct objects. But you're a mathematician and you care about mathematical objects like vector spaces and groups and rings, and you don't really care about ZFC objects. But in your mathematical practice, you've found that you've been forced into like occasionally having two representations in ZFC, but they really are of the same idea. Like there's one real mathematical thing that these two representations um, are really just that thing. But it's sort of impossible to cross this line because that's the kind of uh, really difficult thing about foundations is we have this sort of vague idea of this platonic world that we can never access. Um, and so, like, one reading of this is maybe like ZFC is just a bad foundation, and we need to find a foundation that, like, in the world of that foundation, the only like every single piece of data, everything in that foundation is itself a distinct mathematical object, and you don't have like multiple representations of the same object. Um, but yeah, that's really hard to do, and I guess the uh, I guess the way I view the story of category theory is sort of learning to be able to live, um, to be able to work with things at the ZFC level or at the sort of practical foundations that you already have, um, and being able to sort of observe the situations where you have different representations of the same object. But what category theory does, it sort of systematically tries to identify what is the appropriate notion of sameness of uh, mathematical objects, and that depends on like what kind of mathematical objects they are. Um, and okay, so I want to just give a few, like just one concrete example, which is sort of semi-concrete, and it'll get more concrete as we go. And I'll ask you a question about it in a second. Um, is there any questions about what I've said so far already? Okay, great. Um, so let me draw two. Oh, there's a chat message. Okay, great. Um, let me draw two mathematical objects. Now, most of the mathematical objects that I'll be concerned with are not just sort of uh, like single units of data. Like the number two is just sort of like an atomic thing. Usually, category theory works best when you have collections of things that have structure in them, and like there are I think there are more things than that in category theory, but this is sort of what we're going to be focusing on mainly. So let me draw two structures. And the first one, I'm going to call it Z, as in the integers. And the next one, I'm going to call 2Z, and that's the even integers. And so I'm going to draw this as an object. And this one also as an object. And like this is just sort of one representation of it, I guess. I'm exhibiting a certain structure on these. And so what I'm going to do is I'm going to put I'm going to label points by elements of Z. So I have this sort of infinite line labeled by the integers, and it sort of goes off infinitely in both directions. And the same thing happens here. But instead, I only have the even integers, and so on. And so I'm going to sort of argue that like these two objects I've drawn, according to me, they're the same in a particular in a certain way. So what I can say is, if you like what I was saying before is sort of that labels don't really matter, and if you can sort of interchange labels in a certain way, well, I'm going to argue that changing labels is not really is like can still preserve the same underlying idea. So, for instance, if you take this object here and like sort of just stretch it out, or maybe like think about walking closer to it, so you're sort of zoomed in on it, you end up seeing basically this. But sort of what's the difference there um, is that like one sort of gets relabeled to two, two gets relabeled as four, and so on. Zero stays as zero, minus one becomes minus two, and so on. And so one oh, let me draw this picture a bit better. There's a missing arrow for 3. So one analysis of this is that I've exhibited kind of a bijection between the underlying sets, meaning like like you can think about a function that takes in an element of the first thing and sort of spits out an element of the second set, but there's more going on, as is suggested in this picture. So there is structure suggested in the way I've drawn both of these objects, and that's exhibited by the line I've drawn, and also the fact that they appear in a certain order. And so I'd argue that like there are many such bijections I could have drawn between the elements of Z and 2Z, but this one is kind of special because it respects or preserves a particular kind of structure. Maybe it's not just one unique kind of structure, but like, can anyone give any suggestion as to like what I've preserved between these two things? Maybe I'll give a hint. What if I sort of mapped 0 to, if I sent 0 to 2 and 1 to 0? Yeah, someone suggested order and both countable. So yeah, there's definitely some countability element to it. My thinking has only gone to order for the moment, and so yeah, clearly, if I did like what I did with the red arrows, then I would be ruining that order. And so yeah, the point is that like to do this more precisely is to sort of make that structure more explicit in both things, and then make precise the sort of the notion of preserving that structure. And that's kind of the aim of what we're going to be doing.
You also preserved the monoid structure from addition.
Yeah.
I think Chad was going in that direction. He said you preserved 0, which is meaningful in the context of the operation of addition.
Yeah. That's a good point. And by the same token, I've also sort of, you might argue that I've ruined the multiplicative structure if I was thinking there was one there initially, unless I change what multiplication means. I actually don't want to get into that point, but the final point I want to make about this is that is that the in answering this question, it's like, or like the question of when are two mathematical objects the same, or more precisely, are these two mathematical objects the same? The answer to that question is less of a, there's more to it than just yes or no. Specifically, in this instance, there is actually a witness of the positive answer to that question. We're saying yes, they are the same, and here is how to transform the first thing into the second thing, and the discussion about preserving ordering is a matter of legitimizing that as a uh, as a, a transformation that qualifies as a good enough one or something. Okay. Any questions about that?
If you don't mind me inserting a comment, it's also interesting to note that both of these sets become monoids under, well, they become structures with an operation of multiplication, but that is not something that is similar to both of them. They are different when you consider multiplication, because the first one has a unit and the second one does not. So there's lots of kind of implicit structure we might layer mentally onto the picture you drew. I like the way you presented it earlier. And the criteria for which we decide whether two objects are the same is also a way of saying which structure you're supposed to see.
Yeah. Yeah, exactly. And I do believe there is a way of like saving the story. Well, like you can save the story of like saying it preserves multiplication, because you can put a multiplicative structure on 2z kind of just by cheating and changing what multiplication means by sort of like inserting a half into it, and then you're really like just sort of saying 2 is actually just 1. I'm just calling it a different thing. But okay, but that subtlety is exactly what we're going to sort of make explicit now, in being explicit not just about like what the collection is, but what the structures are on those collections. So let's continue. So in the spirit of minimizing prerequisites, I'm going to introduce groups and just give a brief definition of them, in case you haven't seen them before. So Dan was saying monoid just before, and a group is a particular kind of monoid. So a group is a sort of consists of three components. The first thing is a set. The second thing is an operation, and the third thing is a particular element from the set. And although the underlying set is the thing called G, often this entire thing is also referred to as G. And they're sort of used interchangeably, so just look out for that. Okay, so it consists of a set G and an operation circle, which is it's a binary operation that's usually written infix, so between the two things you're multiplying or however you're describing the operation. Takes in two G objects, and it returns a new G object. So the set, the operation, and it has an identity element E in G. And this is actually this is all we really need to know to like classify the sort of sameness the sameness criterion in categories. But there are extra axioms that I shouldn't just leave out for the sake of it, just for completeness. So I'll write them in. So the it's so a group is a set, but with this extra structure, but not just any such set with extra structure. It also, like, part of that structure, I guess, is some axioms that the operation has to obey, which is I'm going to refer to this circle operation as just multiplying. So if you multiply x and y and then multiply the result of that with z, it's the same thing as multiplying x by the result of multiplying x and y. Sorry, y and z. And this is referred to as associativity. And it basically means you can sort of just write things like x times y times z times w without any brackets, and it sort of has a coherent meaning. Then we have whoops, I should have written in G there. Then we have the identity axiom, which just is saying that the identity element behaves like an identity. So if you multiply on the left or the right by the identity, you get back the element that you started with. Then the last one, sometimes written in this form, is for any every element of the group, you can always find a so-called inverse element, which, when you multiply on the left or the right, you get back the identity. And so you might write like x inverse there instead of y. Other presentations of groups often, like, instead of saying like instead of just sort of giving this existence axiom, we'll actually exhibit a function that picks out the inverse for each element. And I don't know, there's probably reasons to prefer that way or not, but it doesn't really matter for this discussion, I don't think. So yeah, this is the inverses axiom. Okay. Now, what are we going to say about this? Okay. So the story of category theory usually starts with noticing this sort of word. I guess I'm saying the story of category theory for like undergraduate students, and the way they encounter it is that they see this word homomorphism in like all different subjects. And it sort of is saying the same sort of thing. And I guess you end up sort of that leads you into category theory, I guess. Anyway, let me just state what a group homomorphism is, and then I'll come back to the previous example and make it more precise in this framework. So a function between groups, say from G to some other group H, is a group homomorphism sorry, let me rewrite that. If and only if for all x, y in G, so the first group, f of x times y is equal to f of x times f of y. And here to sort of better illustrate what's going on, it's good to write little subscripts that kind of remind you that the multiplication here is happening between two elements of G. So I'm multiplying in G. And the multiplication here is happening in H. So I'll sort of subscript it by H. Because different groups are allowed to consist of the same, of like common objects, but are still allowed to define a different operation. So they define the operation differently, but the group axioms sort of still work out, but in a different sense. Okay, and so this is what a group homomorphism is. But sort of looking at this, it kind of like looks like it's very syntactic the way I've presented it. It's kind of, okay, what a homomorphism is about is something to do with like exchanging f with the operation, or sort of like something like a distributive rule, like a times b plus c equals a times b plus a times c. Like, and maybe that there's sort of like a good story to tell along that line, but I think it's sort of it's not really clear what this has to do with preserving structure, just on the face of this. So I think drawing a picture sort of illustrates it a bit better. So I'll do that on the next board. So did the orb move? Yeah, it did. So if I draw, here's G and here's H. I draw X and Y in G, and then I draw, I don't know if it's better to write, like, to name the third object that they multiply to or not. I'll give it a distinct name. So I've got X, Y, and Z, and the situation is that X times Y is actually just Z. And so this sort of exhibits a sort of component of the structure in G, where like X and Y come together via multiplication to produce Z. So there's a function that takes X and Y and outputs Z, but also it's sort of there's this sort of network component within the graph G. And I kind of think about G as being made up of all of these like three-way relationships between three elements, two of which are inputs and the third one's the output. And so this operation gives you a bunch of relationships like this. And so the idea is, what we want F to do is we say that it preserves this structure exactly when you can draw the same picture on the other side in a sensible way. So we don't have X and Y, we have F of X and F of Y. And here we have F of Z. And they exist with the same relationship to each other. But I've relabeled them. They're not X, Y, and Z. They're F of X, F of Y, and F of Z. And there's the circle there, but remember, it's a different multiplication on the G side and the H side. But once you've drawn this picture, you've actually this axiom is sort of inbuilt. If you want this situation to happen, then, well, notice I've sort of labeled these three things on the H side so that they match the G side. But if I just take F of X and F of Y without knowing this situation over here, the thing I would have written up here is F of X times f of y, because that's what this multiplication does. You get whatever this thing is. So to say that I've preserved this 3-point structure from G to H is to say that f of x times f of y is f of z. But f of z is just another name for f of x times y. So I think that sort of gives a clearer picture of what it means, like why asserting this axiom preserves the structure. What structure is that? It's the structure of the equalities that arise from the inputs and outputs of the operation of the group. I'll just pause there for a second and see if there's any questions about any of that. So the structure is relative to the operation for groups, at least. Exactly. Essentially, I guess what I'm arguing here is that the only relative, like the only structure we have is the one we derived from the operation. So group homomorphisms, exactly, and all they do is make sure that when you have equalities like this derived from the operation on the G side, you can use those to assert corresponding equalities on the H side. Okay, so let me give some examples now. I'll keep going here. So this first one is kind of this. It's similar. This is the situation from the first board, but I guess I don't really care about ordering here. I'm now switching to the sort of group case. So I can exhibit a structure of a group on the set of integers. And the operation is just the regular addition, and the identity element is 0. So you can think about why associativity works, because addition is associative. Doesn't matter the order you add things up. And then identity, well, 0 works as an identity. If you add 0 to something on either side, you get the thing back. And it also has inverses, because you can start with 3 and you can add -3 to it and you'll get 0. Cool. So that's a group. The second group has a different underlying set, which is 2z. It uses the sort of it has the same heart of the operation, but if you're being really picky, you would say that the operation has a different domain and codomain, but it's really the same sort of. It's just regular plus at the heart of it, and it also has the same identity element. And our group homomorphism from this group to that group is going to send an element A to 2 times A. And so I argue that this thing is a group homomorphism. And this is very easy to verify. It's just observing that f of A plus B, so plus on the left group side, is equal to 2 times A plus B. But because of how distributivity works, that's 2A plus 2B. But this is just f of A plus f of B. And so, yeah, in this situation, I've preserved what's the structure that I preserved? It's the one that is derived from the equations. And so, for example, it's the structure of the equations that I derived from the operation. So, what are examples of those equations? Well, you have 2 plus 3 equals 5 on the left side. What does that correspond to under F? Can someone tell me what equation on the right side this corresponds to under the group homomorphism F?
4 plus 6.
Yeah, that's part of it. And then what?
11. Whoa.
Almost.
10, I'm sorry.
Yeah. Okay, cool. So that's it preserves that equation, but also every other equation of that shape. I can plug in any two elements here and the correct element there, and I'll end up with a correct equation on this side. Okay, so that's a group homomorphism. There are other ones. There is, I can say so is, and I'll just briefly say, I could have sent A to minus 2A. I could have also sent A to 0. And this is sort of a hint that structure preservation is a component of sameness of mathematical objects, but it's not the whole story. So yeah, you need more than just the property of being a homomorphism. So if I'll just briefly argue that this actually is a group homomorphism. It just turns every equation into the trivial one. So 2 plus 3 equals 5 just becomes 0 plus 0 equals 0. You can check it. All of the group homomorphism axiom is satisfied because 0 times x plus y is equal to 0 times x plus 0 times y. So yeah, as I said, that there's structure preservation is only a part of the story of when two mathematical objects are the same in category theory. Okay, let's keep going, unless there are any questions. Let me know if there's something I missed. Someone asked what happened in the chat, but I think I missed whatever that was. Okay, my next example is to tell you that, like, okay, the picture from before where, like, I replaced the integers with just the even integers, it sort of feels like, all right, is all there is to this story, is it just like relabeling the sort of constituents of the collection? It can get like it can get plenty more complicated than that. Like maybe at its heart, it's sort of the same thing if you sort of blur your eyes, but it certainly becomes like complicated enough to not just be sort of an obvious relabeling. And so here's an example where I'm not just sort of replacing the underlying set and doing some simple bijection. I can start with this group, which is all real numbers with addition and 0. So similar to before, but now I've got all real numbers. And here's another group. It's just the positive real numbers, so not including 0. The group operation is multiplication, and the identity is 1. And the map here, these groups are actually okay. I came up with this example off the top of my head, so I'm I haven't overlooked something, but I'm pretty sure these are isomorphic groups. And I have a map in mind. Does anyone have a suggestion as to how we could map between these groups in a homomorphic way. Yeah, exponentiation. Cool. So what I'm going to do is send x to e to the x, and this, well, let's verify that this is a homomorphism. So if I start with g of x plus y, I get e to the x plus y. But this is just the same as e to the x times e to the y. And that's exactly g of x times g of y. So clearly, like, these operations are certainly, they have a very different flavor, but you could argue that they are different things. But in the context of this group, and in the sort of conceptual level where you're just seeing the group structure, the argument is that, like, you cannot meaningfully distinguish between these two mathematical objects because they have the same equations. It's just that you've uh, you've got different you've got different elements, or maybe just different names for the real abstract group elements, and you've got a different way of thinking about the operation. So on the left you're doing addition, on the right you're doing multiplication. But it's this map G that is sort of explaining why these aren't so different. And really, if you look at the sort of abstract network of relationships between the objects that you get out of the operations on both sides, they really are the same group structure.
Very innocent question, Billy. So you said the same equations. So two mathematical objects are the same if the same sentences are true of them?
Yeah,
Is that the same as the notion of categorical sameness, or is there a gap?
Are you getting at somewhere? Do you have? Is this more of a comment than a question?
Well, I was going to save this until the end, but I was going to ask you: were they called the hyperintegers? This non-standard model of arithmetic that we looked at.
Oh yeah.
Yeah, there's an interesting sense in which that's the same as the integers because the same sentences are true, but not the same in the category theoretic sense, right?
Yeah,
not,
so
not
I guess
the same objects.
The way you get out of all of these tight spots is you say that sameness is always parameterized by context. So there is no absolute sameness, and these are certainly different things in the sort of global sense, where all the sort of global environment where all mathematical structures exist. And yeah, I guess it's sort of like, I don't know if it's sort of being too non-committal to just sort of abandon equality altogether and just have a notion of like same subscript group or something.
Well, yeah, I guess it's a much less ambitious notion of sameness than you might aim for as a logician, right? But it's also, in some sense, more useful. It's very straightforward, the categorical notion of sameness, and from a certain point of view, also a bit naive, I suppose you could say, if you think about non-standard models of arithmetic or something. But it's still very useful.
Yeah, I think with the non-standard model thing, like you would say something like same subscript first order or something. Yeah. Okay. Moving on. So I said, yeah, I mentioned before that, like, okay, preserving structure isn't enough, because you can have homomorphisms, but like in the situation of this sort of sending everything to the identity element that I had on the previous board, just send every object in G to the 0 in H. Yeah, you're kind of these 3-point relationships still exist in H, but like the sort of edges are a bit of a lie sometimes, because sometimes they collapse into the same object. And yeah, and so you can collapse the entire collection into like a single object within the collection on the right, or maybe you can sort of collapse it a little bit or something. That there's kind of there's a broader world of possibilities of what can happen for different homomorphisms, and we will explore that more next lecture, I think. But I'm going to give you the fix now that allows you to extend this or use this preservation of structure to sort of achieve the sameness criterion. So I'll define now the notion of isomorphism. So a morphism in a morphism F from some object A to B. Actually, I guess I should write this as this is in the Hom set of morphisms from A to B. In a category C is an isomorphism if and only if there exists a morphism G from B to A satisfying two rules. So such that the composition F composed with G, that is the identity morphism on B, and also the other direction. That one is the identity morphism on A. So I think a picture helps here a little bit. There's our objects B and A, and here's our morphism F and the morphism G. There's the identity on B and the identity on A. Oops. Should draw the arrow. Okay, and so this is the sort of definition of isomorphism that that works for every category, and this corresponds to in the category of sets. If you the canonical example of this is in the category of sets. This says that these functions are inverse functions in the way that you usually understand inverse functions. So if we think about this in the setting where A and B are sets, then to say that, let me change color. To say that F composed with G applied to an element of the set capital B, if F composed with G is the same thing as the identity, if you apply that to B, you should get back B. And just evaluating what composition means in the category of sets, it means you apply G to B first, and then you apply the result of that. You apply F to the result of that, and so that's saying that the thing you get back should be what you started with, which is B. And I could write the other rule with using with G composed with F. So drawing a picture for this, you have your sets A and B and the elements. And we're saying that if you apply F to some element here to get something here, then G will always bring you back to the original one. And so yeah, it's important that coming back to structure preservation, just having any two morphisms, one from A to B and one from B to A, suggests it's possible to preserve structure between these two objects in both directions. But it can't just be any two objects to get an isomorphism. You need to be able to like they need to be opposite to each other, which has a clear meaning in the category of sets, but it can sort of have a more abstract meaning in other categories. But if I come back to the example where I send everything in G to 0, that homomorphism there isn't an isomorphism. And the situation is that, if you'll excuse me, I'll just erase what I had here. What's happening is that we have everything in A just sort of gets collapsed down to a single element, even though there are other elements out here. And basically, so we have our morphism F that goes that way. There's no way to we can exhibit morphisms from B to A maybe, but we can't do it so that you satisfy both of these equations. I guess which one of these are we gonna fail at doing? Is it both of them or just one of them? Well, we're going to fail at the first one because, sorry, I mean the second one, because if we map from A into B, some element of A to B, we end up with that single identity element. But we could send that identity element back to A, but that will ruin the fact that this second thing is also gets sent to that identity element, and the map G can't send the same element to do two different objects because it's a function. So let me just check the chat. All right, I should have checked.
If you don't mind me inserting a comment here, it's good to talk about sets in order to illustrate the content of the equations, but it's also an appropriate place in an introductory course on category theory to make the following comments as well, that you shouldn't really think about the objects of a category as sets and pay too much attention to elements, because the elements of the sets, the objects, aren't expressed. There's nothing about them in the language of category theory. It's about morphisms and composition. And a few notes: even if your category, usually the objects are structured sets like groups, and often the functions, the morphisms rather, in a category are functions that satisfy some conditions. Not always. And that is the the morphisms may not be functions between those sets. And even if they are functions between the underlying sets of the objects, it may not be that composition in the category is composition of functions. So this stuff in orange is an illustration, but one should be careful to note that this isn't the only kind of category that one can define. Even if in principle, in the underlying foundations, everything is a set. So the category, its class of objects, the elements of that are sets, if you're taking ZFC as your foundation. So in principle, you can talk about the elements of those sets, but they may not be relevant to working with the kind of propositions that we just discussed.
Yeah, thanks for making that point. And I guess, I'm sort of using the sort of structured sets idea to illustrate things, but really the reason that I haven't given examples of other kinds of things is I guess my area of expertise hasn't extended far enough into that area to say something confidently about it. So thanks for saying it for me.
And regarding Chad's comment in the chat that running away from sets to just get back to sets. Yeah, it's kind of a deep point in some sense. So, well, yeah, maybe that's a topic we can discuss at the end.
Yeah, I guess the sort of view I'm taking is that like the sets are there, but we can be more productive if we operate above the sets and speak of the morphisms instead, instead of the sets, even if they are there. So yeah, you will notice that all of the definitions, they involve like the constituents of the category are the morphisms. They're like the objects are really just kind of I don't know, window dressing. Like maybe that's not the right way to think about it. I kind of think of them as really the morphisms are just kind of domino pieces or puzzle pieces, and the objects just tell you that they're just sort of a system for describing when you can connect one morphism to another, i.e., like plug them into the composition function and receive a new morphism as a result. Okay, let's keep going. And we're going to move on to the next section of boards.
There's more chairs here.
Yeah, I think I should add even more chairs as well.
I don't know if you saw Riley and somebody fighting over a chair earlier.
Yeah, you got to be quick.
I'm not giving up my chair.
Okay, so let me just read what I've written here. Okay, I think category theory made the the category theory. The person made the observation that there's they said something about injectivity and talking about the codomain and the image, which this point about bijections, isomorphisms, and injectivity and surjectivity will be more explored next week. But on the point of collections, of structured collections, here's an example that illustrates that having a bijection, i.e., having sort of two inverse maps between the underlying sets, is not enough to have isomorphisms. You must preserve the structure. Not all bijections are isomorphisms. Probably you can even say that most bijections aren't isomorphisms because there are a lot of bijections. And structure must be preserved. I guess I don't want to spend too much time on this. So if you're not familiar with these concepts, I don't want to expand on it too much. But here is a sort of bijection between two groups. The first thing is the direct product of the cyclic group Z mod 2Z with itself. And the second thing is the cyclic group Z mod 4Z. Z mod 4Z just has 4 elements 0, 1, 2, 3, 4. And arithmetic is normal arithmetic, but you sort of mod Z. Sorry, you mod 4 every time you add things together. So 3 plus 3 is 2 in Z mod 4Z. And so here is a bijection between these two. So the first group is a direct product, so it has pairs of elements from each group, and addition is pointwise. If you send that to 2x plus y, you end up with this mapping. So 0, 0 goes to 0, 0, 1 goes to 1, 1, 0 goes to 2, and 1, 1 goes to 3. And so F is bijective. There is a one-to-one correspondence between elements of the first group and elements of the second group. And the image of this map covers the entire group on the right. But this is not a structure preserving bijection. And that's exactly because we've got 0, 1 plus 0, 1 is equal to 0, 0. But what this corresponds to is 1 plus 1. Well, on the right, that's equal to 2, but there is no correspondence here. 0, 0 does not correspond to 2. It corresponds to 0. So this is a structure breaking bijection. And I won't write it, but I wrote down that facts about Z mod 2Z direct product Z mod 2Z don't translate to Z mod 4Z facts. And I guess this example alone doesn't tell you that these two groups are not isomorphic. It only tells you that this F is not a good candidate for demonstrating the isomorphism. However, there is a sort of way you can convince yourself that it's not possible to exhibit an isomorphism, and it's this sentence. There exists an element when doubled gives the identity. And this statement, when you interpret it about the first group, is true because you can take 0, 1, add it to 0, 1. That's what I mean by double it. And you get the identity. You get 0, 0, which is the identity in that group. But that's not true on the right side because this is one example where it doesn't happen. But you can take any of... I'm actually doubting this. I took this at face value when I when I read this from somewhere, but I'm looking at this now and 2 plus 2 is the identity. So okay, I think that kind of ruins that example. Is that right? That this is actually true of the thing on the right.
wasn't paying attention. Sorry. What's the issue?
Okay, I wrote down that the thing on the group on the left satisfies the property that there exists an element when doubled gives the identity. But that's clearly not true because you can double 2 and get 0. Okay, this would work if I had. Yeah, okay. I was going to say this works if I replace 4 with 5, but then obviously that you can't even make a bijection.
Is it the case that all the ones on the left satisfy it, but not all of the ones on the right do? Would that be enough?
Oh yeah, maybe that's actually the point. I can write a different sentence. Okay. I can say, okay, I'll write it in orange. Every element doubles to the identity. Cool. Thanks for saving that. Okay, so why does this capture? There's probably a good way to like make this rigorous, but it's the reason why this works is pretty much because I've stated a fact about the group which doesn't depend on like the individual data or the way that the operation was defined. It's sort of, it only refers to concepts that all groups have and allows the interpretation of those concepts to be sort of up to the individual group.
If you don't mind me writing something here. So the categorical way of stating what you're getting at is that elements of order 2 are in bijection with group homomorphisms from Z mod 2Z. Right?
Okay.
For abelian groups, sorry. So I guess you're working with arbitrary groups, but in abelian groups, that's true.
And these are both abelian groups. So.
Right. So what that means is that there's a difference between if you try and map Z mod 2Z into the left-hand side and the right-hand side, you can see the difference in the pattern of the maps that exist, the morphisms that exist, and the compositions between them, so that the categorical structure can detect the failure of there to be an isomorphism between these two, because the two behave differently with respect to morphisms in their composition.
Cool. Thank you. Okay. So now I want to talk about how to identify. Okay. I didn't make this explicit, but I talked about group homomorphisms. And let me actually make this explicit then. The category group, that is a category with groups as objects and group homomorphisms as morphisms. So I've said the sort of game of category theory is collecting these mathematical ideas into this sort of explicit thing, which is the category. And so the practice is to identify what things are the objects and what are the morphisms. And given the definition of a category, you have to pick out the morphisms such that composition works. And you usually kind of get this somewhat for free, like if the underlying data of the morphism is like a function. But yeah, there's a sort of a question of like, okay, if I say have a category of vector spaces or something, like how do I pick the right notion of morphism? I don't actually think I have a good answer to that question, but the point I want to make here is that it's usually kind of easy in most cases to like guess what the morphism notion is going to be. I guess once you've seen enough examples, but I'm going to go through a couple examples. So groups. I won't write this one, but groups have multiplication and an identity element. So morphisms of groups should preserve them. So if you have f from g to h, you look at the data of what's involved and you just try and write down something that preserves either the structure of the equations induced by the operation, or you might have some particular elements of the group that are kind of important, like the identity element. You might say that has to become the identity element in the other group. I didn't actually write this part before because given the group axioms, it actually follows from this axiom. It follows from this. There's a simple argument just using the inverses of the group. Okay, now for vector spaces, they also form a category. Vector spaces have addition and scalar multiplication. And so you can kind of already guess what happens with the addition part of it. So if you have a morphism of vector spaces, say from V to W, is going to have to satisfy the same shape rule. F of x plus y equals f of x plus f of y, and you'll know this as linearity because morphisms of vector spaces are linear transformations. But the other one, scalar multiplication. You've already seen the shape of this when I do it as a drawing, but I'm going to do it for the scalar multiplication one. So here's V, here's W. We have X here. And it sort of is related to this other vector in V, which is lambda x. And it's this map that scalar multiplication does, where given some lambda, there's a map that takes x to lambda x by whatever scalar multiplication means. So doing the same trick of saying, all right, I want the same shape thing to also appear in the structure here. We want f of x and f of lambda x. And between them is scalar multiplication here. Do it in orange as well. And looking at that tells you that f of lambda x has to be equal to lambda f of x. Okay, and so that gives you, those are the two rules for morphisms of vector spaces, and that gives you linear transformations. Okay, here's the payoff of like why I was drawing all those images, because I think it's sort of a little bit contrived for vector spaces and groups, but it sort of I think makes the most sense in categories. So there's a sort of, it becomes a little meta here, and you should recognize that I just gave two examples of categories. So the category of groups and the category of vector spaces. And within them, there are morphisms. And I've talked about what structure those morphisms should respect. Now, I can take those two those two entire things, those two categories. And now I'm going to define a notion of morphism between those two categories. So there is a broader category of categories, and there's some subtlety to that I won't get into now. But I'm going to take the same idea of preserving structure and apply it to categories themselves, just like because they're just like any other object, any other thing like a group or a vector space. Okay, so what is the thing that categories have? Any suggestions? So in parallel to groups have multiplication and identity, vector spaces have addition and scalar multiplication. What's the stuff that's in categories that we need to somehow account for in preserving structure? Yeah, so I'm defining what a functor is and has to preserve, but to know what to preserve, I need to know what structure is on categories. If you've done the exercises, you've written down the definition of a category every day for the past week. Does anyone remember what are the constituents of a category, and what could consist of the? Okay, yeah, there's objects and arrows, so they will they're the constituents, like they're like the X and the Y on this previous board that I need to that are sort of involved in structure preservation. But what's the operation? Like groups have that multiplication operation, vector spaces have addition. Yeah, composition. Yeah, categories are really about the morphisms. And the operation you do with morphisms is you compose them. So categories have they have composition, and there's morphisms, but in particular there's sort of important morphisms called identity morphisms. Every category has them. And so these are the two things we're going to try and preserve. I could draw the picture, but I'm going to first give the definition, because it's sort of unlike these previous two things. Functors have two components to them. So a morphism of categories is a functor, and this is what a functor is. A functor, usually written with capital letters. So a functor f from C to D is my fancy D. Between categories consists of two things. And those two things are both denoted with F. So there's some kind of overloading of notation. So there's, you can think of F as a function from objects of C to objects of D. And so given an object of C, there is an object which we can abstractly refer to as f of x. And then here's the more important bit. So for every pair of objects x, y in the objects of the category C, there's a function. So it's not really two functions, it's like a lot of functions. You have a function for every pair of objects, and if you're being technical, you put like the subscript of the two objects there to be rigorous about this, but you'll immediately drop it in practice. You give it a morphism from X to Y, and you receive a morphism in the category D from Fx to Fy. So this definition here depends on already deciding what the object Fx is and what the object Fy is. So you have to define the mapping on objects before it even makes sense to talk about what the mapping on morphisms is. Okay, actually, what I'll do now is this is the worst because I would have to go to the board over there. I'll think about. I'm trying to think what I should do. Okay, actually, we'll just move. I want to draw a picture, and then we're going to actually write the sort of two rules that functors have to obey once we've drawn the picture. So hopefully you've remembered the data of functors. And here's the picture. Actually, I'll make these nice and big. So here is C, and here's D. And there's this functor F between them. It sends objects to objects and morphisms to morphisms. And the composition one is more interesting. So we want to preserve composition structure. Let's draw a picture of composition, or like, I guess more accurately, draw an example of an equation induced by the operation of composition. So I'm going to draw the objects in orange to sort of make them more in the background. And here's one of our things, F. That's one of our morphisms. There's a third object there. So we have a second morphism from Y to Z called G. And then there's this composition operation, which takes those two morphisms and combines them together by composing them, whatever that means in the category. And you get something here, which I'll call G composed with F, because that's what it is. Okay, so we want to move this over to the category D and have the same pattern appear, and then hopefully we'll get an equation out of that. So instead of, I'll start with X, Y, and Z. But really, they're not X, Y, and Z. They're Fx, Fy, and Fz. Oh, what happened? Fy, Fz. And did I say? Oh yeah. So then when I apply the functor to the morphism F, I call it FF. And to G, that gives me FG. And I want the same shape to appear, so I'll draw this here, and I want this to correspond to F of G composed with F. But again, in the same sort of way that I did the previous situations, in this category D, this notion of composition, there's already composition in D, and so if I apply that and I'm asserting that I get this morphism here when I do that composition, I'm saying exactly that FG composed with FF is equal to FG composed with F. And then the other part is I want to preserve identity morphisms. So if I have X here and I have Fx here, if this is an identity morphism on X, then I want this to be an identity morphism on that object, which is f of X. So that's my second equation, that f of the identity of any object, the identity morphism on any object, should yield the identity morphism of f of X. So that's where those two rules come from. So any questions about that? I'll write down the rules sort of formally, just for completeness. Feel free to ask questions while I'm doing it. Cool. Those that's the continuation of the definition from the previous board. So I sort of reached the 1.5 hour mark, and after this, I had some examples of functors that I was gonna leave as exercises, but I guess I'll say feel free to either ask questions and then leave now if you need to, or just leave now if you have to go. But I think maybe I'll write down those examples so you have something to chew on after this lecture. Any thoughts, questions? Do it for functors now. Do what? As in morphisms between functors? Okay, I'll leave that for Will. The thing is, yeah, this question you can always raise the level of abstraction. There's always a thing that witnesses the sameness between two things, and then you can always have a notion of sameness between those those two things themselves. Yeah, the concept there is of natural transformations, and we'll definitely get to that at some point. Okay, let me just I'll give the two examples now. So, example 1 of a functor is one from set to set. So both categories C and D are the category of sets. So if I tell you what you do with objects, you send an object X. So a set X goes to this coproduct. And I could give a sort of very precise definition of what a coproduct is, but sort of vaguely, it's the set that it's kind of like a union of those sets, but you're able to distinguish between things that are from X and things that are from this set. And so it's just guaranteeing that this sort of unique element here doesn't coincide with any of the elements of X. So the functor takes a set X and just adds an extra thing to it. So how do we then take maps between sets on the left side and then map between these sort of sets with an extra point in them? Well, there's something pretty obvious you can do. You can send any object in X. Well, we need to be able to turn it into an object here, and we can do that just by applying F to it. But if we start with the star object, then we can just send it to the star object here. So it really just hangs around amongst like the star object is sort of stays separate from the set X, and the morphisms you get between these things that are images of this functor just sort of leave the star object alone. Will tells me that this is the maybe monad. So this, if you're here for the computer science, this is your example, and so he might have some interesting things to say about it. Yeah. The second one is a little more involved. I'll actually start on a new board for it. This one is an example. We talked about the double dual in the last lecture, and I think Will wants to keep bringing it up because it's a good example of a functor. And so this one is from complex vector spaces, which we call CVect, two complex vector spaces. So again, these are sort of both self functors. It takes a vector space V and returns the double dual. So in case you forgot, the dual of a vector space is the set of linear functionals, i.e. functions from V to C. So i.e. they're linear in the object that you get from the vector space. And then so just applying this definition twice, V double dual, so star star, are linear functionals from V star to C. So as input, you get a functional from V to C, and you're supposed to output a complex number in C. So is there a question there? Yeah, all good. Cool. So that's the dual and the double dual. Yeah, I think a good point to make here is that, like, oftentimes these constructions, like, I guess it's sort of sad to see, or like when you sort of become aware of category theory, it's sad to see just this map because you know that there's a natural thing that happens to the morphisms between the vector spaces that sort of corresponds to this, but it's sort of being left out of the discussion. And so let's include it here. So if we have a morphism between vector spaces, so a linear transformation, what's the corresponding morphism between double duals of vector spaces? So I'll call it F star star, and this thing is itself, it's a function from V star star to W star star. And okay, what does it do to an input V star? That is a hard question to answer without building up to it. So let me explain let's do it one joule at a time. So here is here's a nice picture of what's going on. Think about F. It's a function from V to W. It's a linear transformation. And instead of drawing just W star, I'm actually going to separate the complex numbers out into its own object. So say if I have H, this is an element of W star. It's a map from W to C. That's what elements of W star are, but they're also linear. What I can actually do here is I can compose these, and that gives me a map here. And that's pre-composition with F. So what I've described here is a way of taking something in W star and dragging it back along F to get something in V star, because V to C is a thing in V star. So this construction, starting with this thing and ending up with this thing, is itself a morphism between W star and V star, which takes something in W star, so an H, and it maps it to precomposition with F. So there's a map there. I can do the same thing again, but now with the dual. So F star is from W star to V star. So I can draw the same sort of picture here, but with stars on there. Say I have some linear functional on V star. So some, I'll call it a phi in V star star. I can do the same thing, but with F star now. So I can map phi to phi precomposed with F star. And that gives me F star star, which is from a V star star. So things like phi turns it into a W star star. So a map from W star to C. And as input, you take a phi, and as output, you give phi precomposed with F star. So it's the same construction twice. F star star precomposes with F star, and F star precomposes with F. That's what they both do. So I can unwrap this definition a bit to show you that what F star star does. So I know that if I apply it to phi in what is it, from V star star, I get something in W star star, which means if I give it an H from W star star, then I end up with a complex number. And if I unwrap definitions here, this is phi precomposed with F star applied to H, which is just phi of F star of H, and that's just phi of H precomposed with F. So this is the thing that you have to work with to verify that this is a functor. I guess this is something I didn't say for the last one too. So I've given you the data of this functor from set to set. In here, I've given you the data of this functor from complex vector spaces to complex vector spaces. And the task now is to verify that it sends identity morphisms to identity morphisms. In this case, in both of these cases, they're within the same category. And also that it obeys this composition rule. And this will be a little like, I think this is the sort of, what you'll find is that there's a lot of symbol manipulation, and that might put you off. I guess this is a sort of, I don't know. It's sort of, I would say that it's kind of difficult and requires some focus, and it's sort of an indication that that this equational reasoning and sort of symbol pushing is a bit more complicated than the sort of underlying ideas, and this sort of points you towards trying to get different representations like string diagrams, which I'm not an expert on, but I hear they sort of alleviate this. But for now, I hope this sort of description and this step-by-step explanation of F star and F star star gives you enough tools to be able to verify that this respects composition. And I'll leave it at that. That's those are your first exercises to do this week. Thanks for listening. No worries. What did you guys? Were both of these you, Dan? The drawings. I like the eye.
Yeah, that's the higher structures, morphisms between morphisms between morphisms.
Oh right. Yeah. So that's like that's like 2 categories and 3 categories, and then eventually infinity categories. Yeah.
Yeah, that's right. And then back on the first board, I think that was Riley probably. Well, somebody was. We had a fight about the notion of equality. So the first line there is of course the definition of equality of sets, and then Leibniz equality, which I think you're familiar with.
Yeah.
That is something Riley's is actually studying, or is part of what he's studying right now. And the string diagram that I put up the top there was, that's the string diagram version of the definition of a homomorphism.
Right. Yeah. Do you have a take on string diagrams or anything to do with my last point about like in general these calculations can be a bit tedious and it's sort of hard to keep track of.
Yeah, for sure. So there's I was pretty skeptical about string diagrams for a long time because I'd done a lot of checking of things in categories and by categories and so on without using them, and felt often that, well, I had a bit of an aversion to them because people often use them in a somewhat imprecise manner, right? So it looks like they're proving something, but then you're in a talk and somebody asks a question and then there's some confusion about whether that move is actually legitimate. So people allow themselves to let down their guard when they're using string diagrams sometimes, right? And that I really don't like. And they blur the line between giving an intuition for why something is true and a proof of why it's true. And I really don't like that line to be blurred. I want both, but I want my peas and my potatoes separate on the plate, you know?
Right. So I guess you have to earn the right to put a string diagram up on the screen. Like you sort of, either you promise that you've verified that this corresponds to the concepts precisely, or you actually you sort of present both things. Like, here's the string diagram and here's my argument for why this truly represents what's going on here. Like as if I had done it with
right. Often the way that's I'll finish the story and then give my take on how they get used. So that was kind of, I like drawing the string diagrams as a kind of mnemonic for the proofs that I'd done beforehand in non-string diagrammatic ways. But then at some point I was writing a paper with a mathematical physicist, and he proved something with the string diagrams in 2 minutes that I don't think I could prove. There was some kind of substitution that you could do that was obvious if you put things in terms of string diagrams, but just is completely non-obvious if you just have a page full of commuting diagrams. And at that point, I was just like, okay, well, I'm outclassed. I have to admit defeat. You know, the string diagrams, one should learn to do them properly and rigorously, but this is a technique that really is more powerful, strictly more powerful than reasoning without the string diagram. So I think there's, depending on the area, I mean, there may be situations in which it is merely illustrative, but there certainly exist, without a doubt, many areas of mathematics and physics, where you are simply not understanding what's going on if you don't use string diagrams. So having said that, I'm of the opinion, and I've taught many courses where I've done this, where you really prove the correctness of string diagrams as a language rigorously upfront. And then you know exactly what you're doing. And then it's as valid a tool as moving symbols like A and B around on the page, right? Where you have conventions, like you drop brackets if you have an associative rule, and you sort of, that's not strictly precise when you're not writing down brackets, but you know deep in your bones with absolute certainty that there's no errors to flow from that particular lax behavior, right? And you can get to that similar state of affairs with the string diagrams, and when you've done that, then I think it's as legitimate to use them in a somewhat imprecise way as it is to use symbols without brackets. And then, I think it's a great and very useful tool.